Right, the next speaker is Matt Harvey, who's the Chief Technical Officer of Accelera for these purposes.
Yes.
And Accelera is an SME, which is a core partner in the Biomed project.
That's right. Thanks, Peter. So, as Peter says, I'm the CTO of Accelera, but many of you here will probably also know me, the different hat that I wear, working for the Research Computing Service at Imperial College. Accelera is, as Peter said, it's an SME that I co-founded around about 10 years ago, which the rationale for that was to commercialize a particular application which we developed, which is called AceMD, which is a classical molecular dynamics application some of you may have heard of, maybe even used. It's very similar in function to NAMD, which Peter talked about earlier, but the distinguishing characteristic of it was that we developed it from the ground up for GPUs, which then at the time seemed to be a very promising technology for high performance computing. And indeed, with this code, we were able to do something which was quite a qualitative change in terms of the level of simulation that we could access for a given budget, because instead of having to use a high-performance computing system of the traditional cluster type, we were able to achieve a comparable level of simulation on just a single GPU, which, although doesn't give us more insight at the level of an individual simulation, we actually were able to obtain much more simulation or level of investigation onto the system that we're modeling for the same amount of cost, simply because GPUs were several orders of magnitude cheaper than comparable HPC hardware. So it played its part in really revitalizing the use of MD, certainly in the biomolecular space, and it led to the possibility of being able to commercialize this activity, to undertake a transitional activity from taking MD out of the lab, where it really had been in use in a very limited scope for almost 2 decades by that point, and apply it in industrial contexts. And when we started doing that, we very rapidly found that we encountered 2 main pain points in engaging with industrial clients. The first was that it was a simple issue of resourcing. Many organizations, though they might have had their own HPC systems in-house, often they did not have GPUs, which were absolutely essential for running our application. And they, furthermore, weren't really predisposed to making a big capital investment in quite a novel sort of hardware for what for them was a speculative activity. So we thought initially that we would address that problem by relying on the HPC resources available throughout the community, through academic centres and other centres. But we rapidly found that although that was technically feasible, as soon as we proposed that to the IT security people inside a pharmaceutical organisation, we really ran into the mud pretty quickly, because it really proved very difficult to be able to provide the level of information security, demonstrate the level of compliance that these organisations needed on the sort of infrastructure that we were providing. So we really had to go back to the drawing board and think about how we were going to remove these pain points and be able to deliver the computing resource that these guys needed in order to be able to take advantage of the sort of systems, the sort of solutions that we were proposing to them. So very rapidly we alighted on AWS as the ideal infrastructure for providing this type of resource. To give you an idea of what this level of resource was, an individual experiment of the type that we typically do. Peter described very ably earlier the type of methods that we're using. So these are ensemble MD methods, which are quite computationally expensive and designed to provide some insight into a binding affinity or a binding pathway or close. The exact details vary depending on what we're doing, but it's roughly 10 to 100 GPU years of computation over the course of maybe 4 to 6 weeks in order to complete one of these studies. So we needed an infrastructure in which we could deliver quite a large amount of compute, but for quite a short period of time, because it's important not just to be able to deliver an insight, but you have to do it in a timely manner. If one doesn't get a result in time to inform some business decisions, say in the context of drug development, a computational study is useful only to the extent that you can use it to inform maybe a synthesis or some other investigation. And so you have to be able to fit this type of analysis into a broader business or development cycle. So timely computation is very important. This infrastructure that we built, this product AceCloud, is basically our software layer, which is very thin on top of AWS, that facilitates and orchestrates the execution of our software on cloud resources in such a way as it's very straightforward for an end scientist to use, and it also integrates quite well with the organizational requirements of the organization's IT department. So, as I said, our goal is to build something which is flexible. AWS provides access to such a large infrastructure that we can scale out very rapidly from running just a single simulation up to hundreds of simulations without having to book any time in advance or schedule resources in advance. They're available on demand when they're needed, and then they go away when the need is gone and one incurs costs only while they're in use. Security, as I said, is tremendously important when looked at from an industrial perspective. So it was tremendously helpful to be able to point to the standards compliance of the AWS infrastructure. And so that effectively avoided a whole conversation about us having to provide software infrastructure or demonstrate to the potential client that our own infrastructure was audited and compliant with the expectations that they had. And all of our software, or AceCloud, runs entirely inside the customer's own AWS account. So there's no third-party software involved. There's no transfer of their confidential data outside of their administrative control. Of course, it's reliable. The AWS infrastructure is highly redundant. As Brendan said, there are many different independent regions and zones. We can deploy into any or all of those at the same time. And because the infrastructure is so large, one can, with a high degree of confidence, know that you will get your results in a timely manner, and you're not going to be preempted by some other user who is using resources which you are contending for. You're never going to submit jobs and discover that they're queuing indefinitely, as they might if you were using your own internal and finite-sized HPC resources. We're able to work in quite a cost-optimized way as well. As Brendan mentioned, AWS has the concept of a spot market, so we're able to place the jobs that we need to execute in whichever region in AWS happens to have the optimal spot pricing. So overall, we're able to minimize the let's say the number of nanoseconds of simulation per dollar that we can deliver this way. And generally speaking, what we need to deliver is to optimize the amount of sampling that we are doing for a given price. in the same way that previously one might have tried to optimize the amount of computation one could do in a certain amount of time on a traditional HPC resource. So here we're really looking at a cost optimization engineering activity. Now, all that sounds really good, but you also need to have something which is, for the end user, quite easy to use. Many of our potential users were very familiar with an HPC-style environment. So one mode of interacting with the cloud through AceCloud is an environment which strives to be as similar to a conventional HPC batch processing environment as possible. But of course, this is just a component in a larger application stack that we have. So for many users of our software, one doesn't interact directly with the cloud resources at all, but are rather executing quite high-level workflows which are transparently or seamlessly executing intensive tasks either on local resources or in the cloud, depending on how things are configured. So to just dive into what the interface looks like, if you were installing AceCloud now and you wanted to start running simulations from the command line, then you'd use a simple command line tool, AceCloud, which performs the functions analogous to the qsub, the qstat, and the qdel that you might have on a normal HPC system. There are a couple of distinctions from a conventional environment that you might notice. The first is that we don't use job identifiers which are given to us by some batch system, but rather we have the ability to use our own identifiers, and those identifiers for each job have a hierarchical structure so that we can manipulate one individual job or a large number at the same time. And this makes sense for us because most of our work is ensemble-based, so sometimes it's relevant for us to refer to an individual simulation and inspect the state of that, but often we want to do collective operations on tens or hundreds of simulations. And digging a bit deeper to look at how it interacts actually with the AWS infrastructure. So Brendan put up that lovely slide that shows the constellation of AWS services. We only really use 3 of those, which is S3, storage system, which is an online, effectively it's an object storage, one can put data into it through the web and then retrieve it again. EC2, which is the infrastructure for accessing compute resources, and then this one, which is best expressed as the box around those two, the virtual private cloud, which is a software-defined infrastructure, a software-defined network, which contains all of those resources that we're creating. So from the perspective of the end user, from their own workstation, when submitting a job to AceCloud, they start off by preparing input files. Well, if you've ever run an MD simulation, you'll recognize those files. If you haven't, it doesn't matter. But suffice to say, you prepare a job, you then submit it, much as you would do a qsub with AceCloud submit. Behind the scenes, this software goes away and it copies all of those input files that you've given it into S3, and it then instantiates a virtual machine running in EC2 infrastructure, which is backed by the GPUs that are needed to run our simulation, and also packaged with our software. This comes through the AWS Marketplace. It's something which is like a canned environment that one can instantiate. Our software then, AceMD, starts up, it copies the input from this S3, it runs the simulation, periodically it puts the results back to S3, then when it's done, it closes down, and the virtual machine which it was running on closes down. At that point, all of the resources in the cloud that you've been using are terminated, so you're really only using those resources when you need them for the simulations. There's nothing persistent here. You're not paying for some compute resource to sit around idle and to be available when you need it. The Amazon infrastructure is sufficiently large that you can be reasonably confident that you can get the resources as soon as you request them, which means that when you do an AceCloud status to see whether you're running jobs, you'll see jobs running or finished, but you'll almost never see them in a queuing state, which is probably something you're very familiar with if you've used an HPC system. So I said that's one way of using AceCloud, but also it's available directly through our higher level software. We make available as open source software something called HTMD, High Throughput Molecular Dynamics. It's a toolkit which we use for building all of our higher level protocols and services. It does everything that you need for MD modeling through the creation of models, the execution of simulations, and subsequent analysis of trajectories. So this is quite a verbose script which you don't really need to know the detail of. Suffice to say that what it's doing is preparing and running a single MD simulation, and the bit in bold shows where the simulation is going to be run. In this case, it's going to run on one's local GPUs on one's own workstation. But say you haven't got any of those, or you want to run a large number of simulations rather than just the one. Well, you simply change that to AceCloud Q, and the software will do everything necessary to talk to AWS, the AceCloud, and your simulations will run just as if they were, effectively just as if they were running on your own workstation. So, saying a bit more about how AceCloud is working from a security perspective, really from how we're using the AWS infrastructure. Everything is happening inside a single AWS account, and that means that no data is coming via any server that we run. There's no web server that's an Accelera web server which is talking to AWS on behalf of the client. All of that communication from the client through to AWS is directly through AWS APIs, which means that you get encryption for free, and if you care particularly about security, every one of those operations is auditable, and you can produce a complete log of every transaction that happens, so you can say with a high degree of certainty who did what, when, and what data moved. And this is just something that is not built into our product so much as something that you get entirely for free, in inverted commas, by using the AWS infrastructure. And as I said, we use we're able to use the spot market for cost optimization. Now, Brendan explained how that works in a high level, but what he didn't mention is that every one of those Amazon zones in AWS, regions and zones, have a different spot price because they're geographically distributed around the world, so there's a diurnal cycle to the demand on their infrastructure. And that means that if one is prepared to run one's work anywhere in any of those Amazon data centers, then you can choose to place jobs where the spot price happens to be cheapest, and our software is able to take a holistic view of all of the Amazon regions, place jobs wherever the spot price is cheapest. So we can be reasonably sure that we're always going to get something which is much closer to the floor of the spot price than we are to the on-demand price for the infrastructure. And that makes a really big cost saving. There's something like a factor of 7 between the on-demand price for resources and what we might get through the spot market. For this type of application, that can be the difference between an activity being cheap enough to be something that one does routinely as part of one's work, against something which is prohibitively expensive and something that you would only do as an exceptional activity. So till now I've described AceCloud as being something which is for running AceMD, and indeed that's first and foremost why we designed it. But once we had this tool, we really rapidly discovered that there was lots of other uses for it as well. Indeed, any computationally intensive task, it simply became the default option would be to add this to the AceCloud capability, so that pretty soon all of our intensive compute activity is something which we were doing on the cloud rather than locally on a local cluster or workstation. And one of the applications which I think shows this quite nicely is a tool we have for producing parameterization. So if you're doing an MD simulation, you need a set of parameters which describe the physics, the chemistry of the system that you want to simulate. There are sets of predefined force fields, predefined parameters for proteins and DNA and solvents and so forth. But if you're looking at small molecules, which if you are doing drug design, you almost certainly are, then you need to go off piece to bit and start to produce a parameterization specific for your molecule. And one way to do that is to fit the force field model against a whole set of QC calculations which describe the electronic structure or energy of a large set of conformers of the molecule that you're interested in. So this is it can be a really expensive activity depending on the complexity of a molecule, requiring a large number of independent QC calculations. So again, this is something which one can either do on one's workstation or on a cluster or again on AceCloud, and it's a simple matter of changing the execution target to tell the parameterization tool where it's going to run those QC calculations. And you can get a really big speed up this way. If you do everything in line, then each one of those quantum calculations may be say 40 or so, depending on the size of the molecule. Each one of those has to be computed sequentially. If you go to a cluster or a cloud, then you can do all of those in parallel at once, so you get a much higher turnaround. And for this type of activity, where you have a small number of parameterizations to do, maybe you're only interested in studying one or two molecules, you can really turn this from an activity which is going to block the rest of your work for several days, if you only have access to a workstation, to getting it done in the time it takes you to go for lunch, if you're able to fully parallelize on the cloud. Someone earlier asked Peter about the possibility of doing hybrid calculations using GPUs or CPUs for MD, and we've taken the view that increasingly the MD layer is something in which there's no particular distinguishing characteristic. The MD that we do is very straightforward. There are lots of different codes which can do MD just as well as AceMD now. So we have support for GROMACS and for AMBER and other MD codes, and really the choice that one makes depends on one's familiarity with a particular code, but also the cost effectiveness of using a particular code, which is a function of the type of resources that you have access to. So GROMACS is something which can run on GPUs or CPUs. If one has access only to CPU resources in-house, then one may choose to use this as well. And it's also very useful to be able to switch between two different codes so that you can be sure that if you see something unusual in simulations, then it's not an artifact of the code, but it's reproducible in two different codes. And that's very powerful in terms of getting some degree of verification that what you're doing isn't being unduly influenced by a bug in a code. And lastly, a natural extension thereafter is to be able to run anything through AceCloud, and so if one sets things up in just such a way, one can run an arbitrary job on AceCloud and choose the type of CPU or compute resource that makes most sense for that job. You can select any instance type from that whole list that Brendan hurt your eyes with. So if you are interested in using it, something which you can get access to right now, it's available just as part of our HDMD toolkit, which you can go and download and install now. If you want to have a demo of it or hand-holding whilst you try installing it, then do catch me afterwards in the break. Any questions?